Right. Good afternoon, everyone, and welcome to the Office of the Chief Scientist seminar series. My name is Andrew Paul, and I'm a science advisor with the office and am your host for this year's fall seminars. So on behalf of our entire office, I welcome you to today's event. In the spirit of reconciliation, I'd like to acknowledge that in Alberta, we are on the traditional lands and gathering places for Treaty 4, Treaty 6, Treaty 7, Treaty 8, Treaty 10, and Homeland of the Métis. And maybe on this day where we all might be looking for a little bit of hope, we can reflect that it's actually less than a month ago from this day that members of the Piikani Nation of Treaty 7 were able to harvest their first bison in Banff National Park in over 150 years. So I think this is a pretty amazing example of how vision, dedication, hard work, and resisting that easy button can actually lead to change. In the keeping of tradition of gathering, these science seminars are intended to provide an opportunity for us to get together, exchange knowledge on interesting science that's happening across Alberta in an open learning and sharing environment. To help maintain our call quality today and the video and audio, your video and audio has been disabled, but to keep that ability for us to share, if you have any questions or comments at any time in the presentation, just please enter them into the chat window. Once the presentation is concluded, I'll read out those questions and comments in the order that they were received, and our presenter today will be able to discuss those. So with that, I'd like to welcome today's presenter, and that is Dr. Celeste Barnes. She'll be presenting on mapping watershed snow water equivalent from lidar snow depth and field snow sample density models. Dr. Barnes is a University of Lethbridge postdoctoral research fellow working under the supervision of Dr. Chris Hopkinson. Dr. Barnes' career started in the world of information technology, and she's applied those skills towards a PhD in Earth, Space, and Physical Sciences, also at the University of Lethbridge. Her research interests are focused on the headwaters of Alberta's eastern slopes, where she uses airborne lidar and government data to develop innovative and cost-effective approaches for estimating water yields from the mountain snowpacks. And with that, Dr. Barnes, I'll turn it over to you to start your presentation.
Thank you very much. Good afternoon, everyone. I'd like to thank everyone for joining in today, as well as I'd like to thank the Office of the Chief Scientist for this opportunity to show my research and what we are doing here in the Alberta Rocky Mountain Eastern Slopes. I do want to acknowledge my co-authors, my supervisor, Dr. Chris Hopkinson, Dr. Brandy Newton from Alberta Environment and Protected Areas, and also Dr. Ryan McDonald from Mac Hydro, who have provided guidance and support with my research. So to get things started, we want to know, why is this important? And what we can do is we can see the Alberta Rocky Mountain Eastern Slopes provide a critical water supply flowing in and through the Saskatchewan River Basin, and it originates in Alberta and flows in through Manitoba. There is high runoff that occurs during the spring melt, and this increases the risk of downstream flooding and damage to cities, towns, roads, and other important infrastructure. When mountain snowpacks have completely melted out and are depleted, there is a reduced downstream river water flows. So along with this risk of reduced water supplies, there's also an increased risk of drought and wildfires. There are heavy demands put on Alberta's water resources, and usage is highly regulated to make sure that there's a sufficient supply to support a growing population and economy, while at the same time maintaining healthy ecosystems. There's a need for accurate information as water supply demands are continuing to grow. And in a future warming climate, climate change is expected to decrease the water supply that we receive from the Rocky Mountain snowpacks. So this presents a challenge for reliable management of mountain-sourced headwaters. So since the rivers draining from the headwaters are a major source of water for populations, ecosystems, agriculture, and industry across Canada's prairies, water resource managers and planners require annual headwater yield estimates to ensure increasing demands are met while responding to potential decreases in the supply due to a changing climate. This was especially concerning last winter when there was no snowfall in the winter months in January and February. Unfortunately, there was considerable snowfall in March and April. And this snowfall and precipitation that happened in the later spring was critical since water levels in dam reservoirs were very low, and it was raising concerns of insufficient water in the summer and fall months. So this high spatial and temporal variability of precipitation and the winter snowpack in the mountain headwaters poses a challenge for accurate assessments. So current operational snow monitoring practice, they estimate snowpack volumes from field samples and monitoring sites that are sparsely located in the headwater regions. There is high spatial and temporal variability of precipitation and snow in mountain regions, and weather conditions, elevation, aspect, terrain, forest canopy cover, they all influence the snow accumulation and melt volumes, which in turn spatially affect the volume of snow within a watershed. So this spatial variability of the distribution of snow in the mountain environments means manual sampling alone cannot characterize these snowpacks, especially when water yields are estimates are needed. Therefore, the goal of this research is to gain a better understanding of the spatial distribution of snow water, especially in the southern Canadian Rockies, and in particular in the West Castle Watershed. And to address this need for more accurate and spatially explicit water resource assessment tools, we developed and tested a combined airborne and field snow sampling framework in the southwestern Alberta mountains. So to do this, we need to model both snow depth and snow density throughout the watershed to obtain snow water equivalent, which is used to calculate water yield. So to begin, let's take a look at where the study area is located. Because elevation plays an important role in this research, each station's elevation is shown. So southern Alberta eastern slopes are located on the western side of Alberta, and government snow monitoring and snow core sampling sites are located within this region as well. So West Castle Watershed is highlighted with the polygon, and this watershed was used to test the modeling strategy for creating water yields. So West Castle is located in the headwaters of the Oldman River basin, and it's approximately 130 kilometers west of Lethbridge. And it's the watershed is on the eastern side of the Continental Divide, and it has a continental climate, and there's large temperature ranges with summertime highs of plus 30, plus 40, to wintertime lows as low as like minus 35 or minus 40. And the drainage from this region flows into the Hudson Bay. So next, let's look at some of the characteristics of snowpacks. So in general, at the beginning of the snow season, both snowpack depth and density increase over time. As the snowpack ages, snow will compact, causing the snow depth to decrease. However, with a fresh snowfall, depth will once again increase. Once the pack starts to melt, snow depth starts to decrease, but snow density continues to increase. So the seasonal snowpack is constantly changing. If we look at the mountain regions, there's high spatial variability in snowpack depth and density. So what does this mean? So snowpack depth and density, they vary with elevation, for example. So in the upper reaches, so elevations above the tree line, you can see the tree line here, where there's no significant vegetation, snow depth will increase, but then it starts to decrease as it approaches the peaks. And then winds are stronger at higher elevations, and they tend to cause scouring and redistribution of the snow as there's less forest cover to trap the snow. So the forest, so denser forests or thicker forests will trap blowing snow, and snow that's in the thicker forest canopies is not as deep or as dense as more open areas where there is no forest or trees. It's mostly because it's sheltered from the wind inside the forest canopy. Snow is also intercepted by trees and vegetation, and so therefore less snow falls inside the canopy to the ground surface. Directional aspect, snow on the northern slopes, it stays longer into the spring than on the southern facing slopes. Snow is redistributed by gravity and wind. So if we look at avalanche zones, large volumes of snow move down the mountain in avalanche prone locations. The snow moves from a starting zone higher up in the slopes, and it travels down the track and settles in a runoff zone further down the mountain slopes. The start zone is generally steeper. The track is characterized by openings in the forest canopy where the snow is actually removed trees in its way. And then the runoff is located further down the slope. And snow that is deposited in avalanche is very compact, and it's generally in the more shallow slope locations at the near the lower ends of the mountains. Snow is also redistributed by prevailing winds. Cornices can form on the ridge, so the snow is deposited on the lee side of slopes. Snow will be deposited in depressions like gullies and bowls as well. And there's less snow on steep slopes, and shallower slopes tend to have deeper snowpacks. Depending on the winter temperatures, snowfall events that happen are during the winter months are dependent on the temperature. So, for example, during the warmer temperatures above zero, the lower elevations can receive rain, but the higher elevations can receive snow. And just as an aside, this would be a great day for an airborne lidar flight, as we're about to see. So the southern eastern slopes are located in Alberta, Canada, and the West Castle Watershed is highlighted with the cyan-colored polygon. And then Government of Alberta snow monitoring and snow core sampling sites are located in this region. So Akamina Pass is located near the US border. West Castle 2 is within the West Castle Watershed. Gartner Creek is just to the northwest of West Castle, and South Racehorse Creek is north of the Crow's Nest Pass. Over the past few years, the University of Lethbridge has conducted research within the West Castle Watershed, and the watershed boundary ends at the stream near the University of Lethbridge field station. So elevation ranges in the watershed are from about a low of 1,390 meters above sea level to a high of about 2,600 meters above sea level. And then you can see these points, these cyan colored points, they're just showing the locations of where my field research team and I have collected snow depth and snow water equivalent measurements. So to start off with, what we need is we need to actually calculate snow water equivalent to get our water yields. And from this, we need our snow density, and we're going to get that from our airborne sampling. And snow density, we're going to get that from the Alberta Environment and Protected Areas field snow sampling that they do every month. So how does airborne lidar sample the terrain? So it's a very effective method for sampling an entire watershed in a relatively short period of time. So the this image here is showing, it did show the plane sending out laser pulses. And so the pulse would be sent out, and then the lidar system receives the pulse, and the system measures the return time. And from that, it actually calculates an elevation above sea level. So this system can send out up to like 1 million pulses per second, and it can collect several points per square meter as it's flying. So the first thing that we need to do is we need to actually plan the mission. And so what we're looking at is we're looking at the area that we want to fly. So in our case, for this study, we flew the West Castle Watershed. So that was our region of interest. And as part of the flight planning, we have to go and coordinate and find flight crews and ground crews to be able to fly the system. So the airborne survey system is it costs in the range of about $3 million. So it's not something that all labs have, and so it usually has to be contracted out. However, Dr. Hopkinson's lab, which I'm a part of, does have a lidar system, and so the lidar sampling activity also requires a plane, the mission pilots, and the ground support who are required to set up equipment for the survey. So now if we look at this to sample snow depth over an entire watershed, one lidar, like one collection technique is to use the airborne lidar. But this is a repeat sampling technique. So it requires both a summertime flight where the ground has no snow and a winter flight where we're wanting to sample the snow. And the snow depth models are created by subtracting the wintertime snow from the summertime DEM. So one of the things that that we have to take into account is lidar coverage within a single flight in the winter months is limited up to a few hundred square kilometers, and that's because of, like lower amounts of daylight. The days are shorter. And so we want to actually be flying during the day, because flying in the mountains is a rather challenging venture when we're flying an airplane, especially if there's updrafts and things like that. But generally speaking, there is surplus aircraft and crew availability in the winter months. But one of the downsides is we may be on standby waiting for optimal conditions to fly, due to the limited daylight, as well as we need very favorable weather. So under correct sampling conditions, we want cloud-free with low relative humidity. And because if there's higher relative humidity, the atmospheric moisture will reflect these pulses, and there'll be fewer points going to the ground and more ending up in the air. And due to the large cost, it may only be possible to have one survey completed in a winter month. So what we get out from that system flying over is a point cloud. So the laser system collects and samples points. So the combined set of points is referred to as a point cloud. Now, depending on weather conditions, there will be points collected that are not actually part of the terrain, which could be, in the air. But for the most part, what we're looking for is we're collecting terrain points that include the ground, the forest, vegetation, buildings, roads, and other features in the landscape. So if you look at this point cloud, it shows the northern end of the West Castle Watershed. So this is a summertime collection, which means that there's no snow. And you can see the Castle Mountain ski hill in this photo at the bottom kind of center of the screen here. So once we receive the point cloud that is processed from the lidar system, the first step is to remove all the points that are not part of the landscape. So that means ones that are in the air. And depending on the flying conditions, this can take a significant amount of time, especially if there's a lot of blowing snow. And so we've got points that are reflected off the blowing snow or the moisture. And so those have to also get removed. So as I had said, the points that we get from the system represent an elevation above sea level, and we use the metric system, so our elevations are in meters above sea level. And the next step, once we've cleaned it, is to create two surfaces, or two models. So one that has only the ground points. Okay, and so this is the digital elevation model, and the second has all the points, and that's the digital surface model. So in the winter, these points can end up being in the sky due to the laser capturing blowing snow. So once we have kind of cleaned the point cloud, the last step is to convert all the points in these two models, and the DEM and the DSM, into a grid. So typically, that means that we will convert the points into grids that are 1 meter by 1 meter in size. And so our point clouds generally have between 4 to 12 points in each grid cell. So for the West Castle Watershed, this means that we have about approximately 103 million square meters of grid cells, or 103 square kilometers, and that represents the entire watershed. So in the winter, the images show typical snow depths in the watershed. So if we look here, this is a valley. So this is at the field station, and we can see that the snow depths are generally more shallow. if we look here at the subalpine, so this is taken when we were on the ski hill, and it shows a 3-meter avalanche probe that has been put into the snowpack, and it's approaching 3 meters. So in this location, there are actually depths that are greater than 3 meters. So we get deeper snowpacks in the subalpine. And then up in the alpine, so this is in the alpine ridge, you can see scouring that happens. But in the areas where there is some canopy and sheltering, we can get snowpacks that are generally greater than 3 meters in depth again. So, and this variability happens within about 50 meters of the area. So it shows, so this shows one of the advantages of using airborne lidar to sample the snow depth within mountain regions. So publicly available snow course data are sparse in the headwaters of the Rocky Mountains, and it covers a large area. So in the southern Alberta mountain headwater regions, it's typical for these government-managed sites to be at mountain, valley, and subalpine locations. So some of these AEPA field snow sampling sites used in this study have significant forest cover. Okay, and you can see with South Racehorse Creek, Gardner. I mean, these are older photos, but you kind of get an idea. This is West Castle too. This is the valley within the watershed, and then we have Akamina. So Akamina it is in the southern part of the province, but it was burnt during the Keno wildfire. And so AEPA have reinstalled this site at the same location, but the snowpack is very different in Akamina after the fire. So AEPA conduct field snow sampling during favorable weather conditions on either side of the first of the month. And so some of these sites can be quite challenging to get to. And so what we want to, they're going to actually probably use a helicopter or a snowmobile to access the site. And what we want to try and do is we want to try and coordinate the AEPA field snow sampling with our airborne lidar sampling mission. And this is one of the airborne lidar mission planning challenges, is to do both activities on or as close to the same day as possible. So now we want to actually look at how we sample the snow depth. So this was myself and one of my teammates doing the snow sampling, but AEPA generally use the same process. So this photo shows how we use the sampling. So we start with an avalanche probe to get a snow depth measurement. And then once we have the depth measurement, we take a snow sampling tube and we carefully put it into the snow column to take a snow core. And what we'll do is we will weigh the sampling tube before we take the core and after we take the core, and then the difference that we get is the amount of snow water equivalent at that location. And so then from snow depth and snow water equivalent measurements, we're able to calculate the density of the snow for that sample. So now if we start looking at the snow density model, remember we got snow depth from our airborne lidar. Now we want to actually look at the snow density, because snow density is not really able to be sampled for an entire watershed. So what we have to do is we have to model it. And so we've taken two, we'll call them deterministic drivers that influence the spatial and temporal density measure variations within the mountains. And so the first one is elevation, and the generally speaking, snow density increases with elevation. And then the second one is the amount of forest canopy coverage. Okay, and again, remember I had said that in areas where where the forest is much thicker, there's less snow, so the snow depth will be less, but also the snow density will be less. And so then what we are going to do is we're going to take our model that we derive, and we're going to go and reduce it based on the amount of forest coverage in each of those grid cells. Now, for the purposes of this research, you can see that this model here has been divided into 3 equal areas, and we'll get into that a little bit later. So the snow density models, there are 2 snow density models that we actually created, and we used West Castle 2, which is inside the watershed, and then the Gartner location, which is just to the northwest of the watershed. So West Castle 2 is in more of a valley, and Gartner is in the subalpine. And we've used those 2 sites to constrain our model. So because it can be difficult to coordinate with AEP field snow sampling with our airborne lidar snow sampling, we tested 2 different snow density models. So the first one we tested was the snow sampling, the AEPA snow sampling that was closest to our airborne lidar flight. And then the second one was using the 30-year monthly mean, the AEPA samples that was closest to our airborne lidar flight. So now that we kind of have an understanding of how LiDAR works and how we actually do the sampling, we'll do a quick look at our workflow. So once those point clouds have been turned into a grid, the flow chart shows the process to take each airborne LiDAR snow sampling flight and combine them with the snow density models and to create our snow water equivalent, and then calculate the final water yield for the watershed. So that's a lot. So let's just break it down. So the first step is to prepare all of the airborne LiDAR derived grids, so both the snow and the snow flights, into a watershed DEM. So we've taken our point cloud, it's now in a grid, and so each one of those 1 meter by 1 meter grid basically just has the averaged points that we've collected, and we're going to actually what's called aggregate. So we're going to average it over a 30-meter area, and we're doing this for the purposes of future phases in the creation of this framework. So the second part of this panel shows how we actually created the canopy fractional cover. So we use, so what we're doing is we're extracting only the forest canopy, so only the trees. And to do that, we use both our digital elevation model, which was just the ground, and the digital surface model, which had all of the points. And then this tool gives us the measure in percentage of how much forest is within each grid cell. Okay, so once we've now got our models created, the first step is to actually create our snow depth. And so what we do is we take our snow depth model, which is our wintertime flight, and we subtract it from our summertime flight, and that gives us only the snow depth. The snow density is created from each for each flight, and then we take the West Castle 2 and the Gartner sampling values, and we use that to create an upper and lower bound for the model. And so once we have that created, once we have the density model, and then we adjust it for our forest coverage, we get our density model, and it's just a matter then of taking our snow depth and multiply it by snow density, and that gives us our snow water equivalent. And from that, we can take each one of those grid cells that we have now has a snow water equivalent in that. And so we basically just sum the snow water equivalent for every grid cell for the entire watershed. So if we now move over to our results, we can see these are the results. So there were 6 flights at different times in the year, starting in February 2014, all the way up to April 2021. So one thing that you will find interesting is the April 2018 had the deepest snow throughout the entire watershed. And this was actually this flight was done near the closer to the end of April. Okay, as opposed to this one, which was at the beginning of April, and you can see much lower snow depths, and the black actually indicates that the pack has actually started to melt out. Another interesting part is we took and did a flight pretty much 1 year to the day apart. So in March 2020 and March 2021. And we can see that the March 2020 had deeper snow than 2021. And the last thing that's kind of interesting is in the year 2021, we actually did 3 snow sampling flights. And you can see the changing progression of snow depth through the year. And generally, there's lower snow depths in the valleys, which is down in here, and then as well as in the alpine areas, which is up in here, so the white, and then deeper snowpacks in the subalpine. Now, if we look at the snow density, this is where it becomes really quite interesting. So this plot here is the 30-year mean or average snow density per month for our 4 field sampling sites. So West Castle 2, Akamina, South Racehorse, and Gartner. Okay, so West Castle 2 within the watershed is a valley elevation. These other 3 are subalpine elevations. So one of the things that you can kind of see, if we look at just the West Castle and the Gartner, so the valley to the subalpine, you can generally see throughout the entire year, there's a general increase in snow density with elevation. What is really interesting now is if we only look at the subalpine sites, if we look at South Racehorse Creek, which is the green, it's only 20 meters lower in elevation than Gartner, but the snow density is quite different. So elevation is not the only thing that is affecting our snow density. So now, if we look at our snow density maps, again here, these are showing the maps for the Model A, which is the closest sampling date, AEPA sampling date to our lidar mission, because it's not visually much different when we look at it. But over the course of the snow season, we can see that literature tells us that density increases with elevation, and that which can be seen in here. So lower densities in the valleys, and then higher as we get higher up in elevation. And the again, the April 2018 had the highest snow density values. Our two March ones, 2020, had the higher snow density. And then again, the progression, if we look at through 2021, we can see the density progression through the year. If we look at our snow water equivalent, again, we can see April 2018 had the highest snow water equivalent throughout the watershed, and there were lower amounts of snow water equivalent in the valleys, and same in the alpine areas, but higher in the subalpine area. And again, we can see the progression from our 2 March, as well as the progression through our 2021. And you can see that in April, the pack is actually starting to melt out, which is why there's very little SWE in the April mission. So let's quickly look at the water yield and what the kind of water years were. So this is taken from our Gartner snow pillow that they have. So this is a continuous reading at a single point of how much snow water is recorded through the year. Okay, and you can see the black circles are where we've done our missions. And one of the disappointing things is that the year that we actually did our 3 different missions had the least amount of snow and snow water throughout the whole year. And here we can see our April 2018 had the highest amount. So if we look at our results, so this is our yields. So if we look at our closest sampling date, we can see our April 2018 had the highest amount of snow water yield. Our April 2021 had the lowest amount. If we look at using the model with the 30-year mean, again, the April 2018 had the highest one, and this time the March 2021 had the lowest. But you can see that there's an issue. Only one of the sampling dates, of our airborne lidars had both AEP and our sampling taking place on the same day. So if you look here, there were some of these samplings were as much as 6 days, up to 9 days before or after when our actual sampling had actually taken place. And now this is where that breakdown of the 3 elevation bins comes in, because we can see that the higher elevations actually produce the most water. Now this also includes the water the alpine area, but it captured the highest, or was the most productive area within the watershed. So to wrap up, the rationale behind this research was to obtain a better understanding of the spatial and the temporal distribution of snow water in the Canadian Rockies, and in particular in the West Castle Watershed. And it was to develop a cost-effective framework for estimating water resources, as well as gain a better understanding of where the most productive regions were. So with the 6 single point in time snow water estimates we created, we find that all we need to create these estimates is we need an airborne lidar flight, and we need our AEPA partners. We need their field snowpack sampling. And we have gained a better understanding of the distribution of snow water within the watershed. So the most productive area or elevations were between 1900 and 2200 meters above sea level, which is in our subalpine. So the next steps are actually to scale up the snow monitoring framework to the entire eastern slopes. So I'd like to say a special thanks to the Alberta Environment and Protected Areas for their field snow sampling. I also want to thank Maxim Okermenko with the airborne lidar flight operations, as well as my ground crew and the people that I dragged all around the sides of the mountains to collect sampling as well. And with that, I'd like to thank everybody for joining in, and I will turn it back over to Andy.
Wonderful. Thank you. Thank you so much. And lots of kudos on the chat there for you to look through as well. So again, thank you everyone for joining our science seminar today. Our next seminar is going to be on Tuesday, November 19th. It's going to be Dr. Irina Creed from the University of Toronto, and the presentation will be on harnessing the power of wetlands, nature's blueprint for climate solutions. If you're not on the mailing list for these science seminars, please send an email to the Office of the Chief Scientist. That's at epa.ocs, and that's at gov.ab.ca. And with that, we'll end our presentation for today. Thank you, everyone, for joining us, and look forward to seeing you in a couple of weeks.